By now, you guys all should realize that the vision is by 2023 for us to launch commercial operations on Uber Air, and that operation will be piloted from day one. You should also be aware that there is a shortage of commercial pilots currently, and the ambitious scale that we talked about yesterday may seem out of sync with reality, and it is unless we do something to affect that. You need to realize, however, that we are not taking the approach of just figuring out ways to increase the labor pool of pilots to serve the Uber Air network. What we're doing is taking a more responsible and principled approach to the problem and determining what technology needs to be developed, tested, integrated, and certified to meaningfully change the workload in the cockpit, to significantly reduce the workload and simplify the pilot experience, which then can translate into new types of training methodologies and a new type of pilot certification in the future. But what we're going to talk about today, and we have an expert panel to talk through this with us, is the technologies that are really enabling this and the path to certification of those technologies that will be the precursor to any change in the pilot certification. Greg will talk a little bit more about the roadmap that ties it all together at the end. So with that, I'm going to introduce our first speaker, and each one of our speakers is going to give their own presentation up here, and if we have time for it at the end, we'll take some questions. So kicking this all off is going to be Jeff Greenwood, who is the chief pilot at Bell, and he leads all of Bell's training, production, and experimental flight test pilots. He joined Bell in 2006 after 14 years in the Marine Corps, and he's going to talk to us a little bit about the unique Bell perspective.
Thank you, Stan. Thank you. All right, so Stan asked me to come here today to give a pilot's perspective. Can I go now? So what he specifically asked me to talk about was the cockpit environment, workload, what Bell has learned to fly-by-wire, and how we plan to bring that to bear in this market. So I'm going to break the cockpit up into two pieces. I'm going to talk about the cockpit itself, and I'm going to talk about controls. So this is a cockpit. Probably reminds everybody here of their car. Me either. It's a busy place. This is a fairly typical, it's a 412 EP. There are 24 gauges the pilot needs to see. There are 40 switches that he has to interact with. He's got to take that round dial information on the gauges and turn it into information about where you are in 3D space in relation to where you left, where you're going, an obstacle, something along those lines. You got to take that information and turn it into what you know about the health status of your aircraft. Do I have enough fuel? My engine's good, gearbox good, etc. Now we're getting better. We've got glass cockpits. We've got synthetic vision. We're going to integrated systems, which all make it easier. But when we train a pilot, we train them to fly that. And then the other stuff comes later. So that takes a while. Then you got to learn how to control the aircraft to make it go where you want it to go, which isn't always easy. Again, unlike your car, which has one control to go left and right, one control to go fast, and one control to stop, and I got to say, in my practical experience, I've never had to use all three of them at the exact same time. Might be fun in a rental car, but not mine. A helicopter's not quite like that. If I want to accelerate, I got to add some power with collective, I got to push the pedal, and I got to push the nose over a little bit. If I do it just right, I'll go where I planned on going. So then once you've learned to read the aircraft, control the aircraft, you got to put it all together and you got to execute a mission. So say you're just going point A to B here in LA. Got to talk to at least 3 people. Where I left, where I'm going, probably somebody in between. Means I have to change the radios. I'm going to have to write something down because those people are going to give me directions. I got to interact with the nav system, whether it's a moving map in the aircraft that's integrated, my iPad, or maybe a paper map. And I've got to do all that while I'm doing that other stuff from the first 2 slides. So again, it's a busy place, and if you're a lazy pilot like me, I don't want to do most of that stuff. I prefer somebody else do it for me. So Bell, we've been doing fly-by-wire for a while, and we've learned quite a bit from it. We know we can make flying easier. Here's where I just saw my boss walk in, and here's where I tell Mongo's story. And if you think of me, Mongo, you're on the right track. He was a squadron CO in Iraq with V-22 squadron. One day a sandstorm blows in, and it's the can't see your hand in front of your face type sandstorm. Shuts everything down. And unfortunately, Marines, when they get bored, they tend to play with poisonous animals. So up on the Syrian border, a Marine gets stung by a scorpion. They can't put him in a Humvee because they don't even want to drive. Mongo says, I got a V-22, I'll go get him. So he goes out to flight line, gets in the V-22, adds power, comes up to 20-foot hover, hits his departure button, aircraft takes off, converts, gets up to altitude, aircraft flies to the descent point, types in the LZ, aircraft descends, pulls into a 20-foot hover, he pulls power back. Do that going back, they saved the Marine's life. But what did Mongo do? Added power, typed some stuff in, and reduced power. So we can already do a lot of this. Hovering, one of the harder tasks to teach and to accomplish as a helicopter pilot. It's, anybody's ever taught their kid to ride a bike, it's kind of like that as an instructor. You can't really teach them to ride the bike, you're just there to catch them when they fall. Hovering, I can't teach any of you to hover. I can just be there when the aircraft starts to roll off and try and catch it and save the day. In the 525, I can teach all of you to hover in 5 minutes because the aircraft hovers for you. You hover by taking your hands off the controls and let it do it. If I overlay translational rate command on that in another 5 minutes, I can teach you how to maneuver the aircraft in a low airspeed environment. If you want to go right, you push control right. When you want to stop, let go. The aircraft stops. So we know we can make it easier, and we know that what we want is the pilot to tell the aircraft what to do and let the aircraft figure out how to do it. That airspeed example earlier, well, now you no longer have to do all that stuff. I want to go faster in a 525, I push the cyclic forward. When I get to the airspeed I want, I punch a button, let go. The aircraft holds the airspeed, it figures out the power, it figures out the trim, it figures out the pedal that needs to go in. So Bell sees eVTOL as an opportunity. It's an opportunity to not only change what we fly, but how we fly and how we interact with the aircraft. We know it's got to be intuitive and it's got to be simple. The controls, we're going to build off what we've learned in 525, V22, V280. Instead of controlling pitch, attitude, or pitch, roll, and yaw, instead we're going to have the pilot control flight path. He's going to tell the aircraft what he wants it to do and let the aircraft do it. The cockpit, got to get rid of the round dial information, make it pictorial, make it easy to read, intuitive. Automate things, automate comms, nav, basic airmanship. We know, or we feel that we can do this, we know we can do it, because our eVTOL is going to have the fully autonomous capability from day one, but we recognize that due to public perception, the regulations, building confidence in the safety and the reliability of the aircraft, that we're going to have a mission manager on the aircraft. The job of the mission manager is going to be tell the aircraft what to do, and we're going to let the aircraft go do it for him. So that ends it for me. I'm going to turn it over to Stan. I hope you all had a chance to go to our Bell experience out there. If not, I would highly encourage you to go do that. Thank you.
Thanks, Jeff. Thanks, Jeff. All right, Justin. Justin Paynes is a test pilot at 2XL Aviation and has been flying for over 30 years, both in the UK Royal Air Force and as a private experimental test pilot, spending a significant amount of his career focusing on VTOL and Vtol aircraft, including the X-35. Thanks, Justin.
Thanks very much. So, try again. Bit of a complimentary talk on what you just heard from the rotary wing perspective, looking at fixed wing VTOL and as I put it there, radically, and it's radically transforming the safety and simplicity of VTOL flight operations through flight control. And I'll take you back into history a little bit, if I may, just very briefly, to look at the birth of VTOL for powered lift platforms was in the military, late 50s and through the 60s, US, UK, Europe, Russia, Soviet Union, all working on VTOL fighter concepts. Really only one aircraft, arguably not including the Russian Yak, really only one aircraft that was successful, that's the Harrier. And the breakthrough at the time in flight control is that the Harrier could be controlled with only one extra lever. So you had stick throttle and one extra lever, which was the nozzle lever. So it was quite a breakthrough, and by the standards of the times, for VTOL, very, very simple. Unfortunately, however, the capability, the operational VTOL capability came at a price, which you see there. High accident rate. If you look at takeoff and landing regime, you're talking about a 9 times accident rate compared to comparable fighters with a conventional takeoff and landing, but similar operational role. Order of magnitude higher accident rate. High training burden. Takes about 8 months to, or took about 8 months to put a guy through the Harrier training, compared to about 3.5 months for a comparable conventional fighter. Operational limitations. If you compare to the helicopter, we couldn't we couldn't recover to land in so bad weather because the cockpit workload is sufficiently higher that we had to limit the weather conditions that people could fly in. And we had to restrict our pilot choices to the better half of any graduating class from flight training. So we had to only take the better pilots because of the difficulty of flying the aircraft. So quite a few limitations there. There's just one example of a perfectly serviceable operational aircraft with a guy just trying to land it and what happened. It's a video I took the clip from. I can show it to you later if you're interested. So not good, and particularly not good for the 21st century. And what the military set out to do was reverse all that and redress those problems. So about a 20-year government research program in the US and UK collaboratively set out to change all that, and succeeded. We achieved some fairly amazing results in simplifying the flying task, increasing safety, and reducing training. And I'm just going to show you a little bit about that as we go through. But it is possible. The bottom line is, summary up front if you like, it is possible to radically, and I mean radically, increase the safety, reduce the training burden, and increase the effectiveness of the same pilot. You can take the same guy, whether he's skillful or unskillful, and radically improve his safety, reduce training, and increase his effectiveness. And you can do that quite simply through flight control, some of which Jeff has just touched on. How do we do it? So we ended up, so this is the summation of 20 years of and many millions of dollars of government research programs. And we came up with the concept of unified control. So in unified control, if you look on the slide there, you pull the stick back and you climb, you go higher. Houses get smaller. Push the stick forward and houses get bigger, which sounds pretty familiar, right? But the difference is you get the same response at 5 knots or at 500 knots. You do the same thing in the hover or in forward flight to get the same axis of response. Throttle goes forward to go faster, comes back to go slower, or in the hover to go backwards. And this was proven through our research to be the optimum, low workload, low training, and most importantly, low risk of pilot cognitive error. What we found with other strategies which involved a change of hands effectively is that we saw pilot mistakes being made, pilot cognitive error, which is one of the things that led to so many accidents in the Harrier. Now, this is a very, very top-level summary. A lot of details omitted, of course. So please do ask me later. I'd be very happy to talk about it. But very conventional approach. The trouble was, this is a totally alien concept to any Harrier or helicopter pilot. Absolutely alien concept to any of them. And I'll talk what this meant to us in a moment when we tried to get this adopted in the Joint Strike Fighter program. Some important display functionalities, and I'm not really going to go through those. I can explain offline. We haven't really got time, but very simply, plan form velocity vector with a predictor and properly scaled. So all the pilot has to do is he moves his plan form velocity vector predictor in the screen, and when he gets it over the pad, he lets go, and that's where he's going to stop. As I said, I'm very happy to go through a lot more details offline with anyone. Very difficult to cover all the details, obviously, in a short summary. So it was a radical proposition. So what are you telling me, as a Harrier guy, I've got to pull back on the stick and the engine's going to wind up? Well, yeah, that's exactly what happens in the F-35 today. So we did face a lot of opposition from the old guys. Well, I wouldn't say the old guys, the young guys too. We faced opposition from anyone who had 1,000 or 2,000 hours an Harrier or a helicopter because it was so radical a proposition. But we weren't designing for the old guys with 2,000 hours. We were designing for the PlayStation generation. We had a lot of very good data, and in the end, we did win the day with a lot of bright minds supporting us. But I have to say, and it did feel a little bit like that at times in the program, became a very, very emotional debate, and very nearly went the wrong way just because of the emotion that was involved. It's hard to change established traditions. So what are the technologies required? And they're not many. First of all, you need digital flight control, of course, fly-by-wire, with integrated flight and propulsion controls. The two should be a part of an integrated flight control system because, of course, propulsion in Vtol is an effector. It's like a control service. It impacts what happens to the aircraft, attitude, etc. It's not just for adding energy. So integrated flight and propulsion controls, you obviously need accurate position and velocity data. We've had that for years with GPS inertial systems. And you need about 1990s vintage computer processing power. So you can see we're a lot further ahead. I mean, all of these things are very mature technologies. They're routinely used in the drone world. They're mature. They're all over the industry. There are multiple providers that can give you any of those three enabling technologies. So this is known stuff, and it's out there, and it's available to be used. And really, the only thing you've got to focus on, which is platform-specific, is obviously you've got to look at the redundancy issues to make sure you've covered redundancy. And we're not looking at augmentation and a fallback here. We're looking at an all-up redundant system that always operates the way it's designed to operate. And no control augmentation, stability augmentation, and a fallback, but actually the fundamental flight control system has all this capability, and you just build in the redundancy in the sensors and computers that you need. So how did we do? Joint Strike Fighter is now flying in service. The Marines are flying it. The jury's now in. And we, fortunately, can conclude that we got it right. Unequivocally good reports from the front line. People saying, why would you do it any other way? This is obviously the way you fly VTOL. Training being radically cut. Non-VTOL experienced pilots going to sea, doing takeoff and landing from a moving deck without any prior sea experience. We got non-pilots flight. That's our research airplane that we did all the work on. It's a two-seater, and we got non-pilots, program engineers, program managers. We had the F-35 program manager fly a landing, and also one UK national news reporter. And if you'll excuse me, I'm going to play about a 1.5-minute clip from the national news in the UK. It's quite amusing.
Now, the RAF claim that flying the latest Harrier jump jet is as easy as driving a car. Well, we were a bit doubtful about that, so to put it to the test, we sent them our science editor, Lawrence McGinty. Now, Lawrence actually can't drive a car, but despite that, they still let him loose at the controls of a multi-million-pound jet fighter. Here's what happened when Lawrence became our very own Top Gun.
I walked across the tarmac with test pilot Chris Gopka, but I still couldn't believe it. They were going to let me fly a Harrier. As they strapped me in the rear cockpit of the two-seater experimental plane, I kept telling myself the new control system made flying the Harrier easy.
I'm fat, I'm 50, I'm trussed up like a chicken, I can't even drive a car, but I'm going to have a go at driving this.
The new system is easy. Push forward on the left grip to go faster, pull back to slow down. On the right, forward to go down, backwards to climb. Left to go left, right to go right. After 5 minutes of flying the Harrier, then came the tricky bit, bringing it into a hover and landing vertically.
Here we are, we're jetboarding an aeroplane which is quite spectacular, and we're at 100 feet. So all I need you to do now is push forward on the right stick. Okay, just ease off on that rate of descent, thank you. Just keep coming down there. There you go, that's perfect. Keep coming down, keep coming down, keep coming down. We're on the markers, we're close enough to the markers for me to be happy. Keep coming down, keep coming down, keep coming down, keep coming down, keep coming down.
And you've got it now?
I've got it now. Many congratulations.
I don't believe it! That was, wow. How do you find sex interesting after this?
Anyway, so the final slide then, just to finish out, I thought you'd like that. Takeaway points then, digital integrated flight and propulsion control enables the most challenging flight task to be made child's play easy. Since this program, incidentally, it's been done for naval carrier aviation as well. Child's play easy. We need to be careful about human predisposition, paradigm, doing it the way we've always doing it, because that's how we fly Vtol, that's how we fly rotoring, whatever it is. We know the best way. We've done the research. We've got the results. We know the best way to apply the technologies. Unified control, we've got a lot of display knowledge as well. And the enabling technologies are pretty much mundane and routine today. Be happy to answer any questions afterwards. That concludes my presentation. Thank you.
Thanks, Justin. All right, Justin's going to be followed by Wes Ryan. Wes has been at the FAA for 15 years and has helped lead emerging technology and initiatives in avionics, light sport aircraft, electric propulsion, and unmanned aircraft. His past efforts were instrumental in bringing safety-enhancing glass displays, GPS moving maps, and envelope protection autopilot technology into the GA aircraft. For 5 years, he's been actively participating with NASA to identify a regulatory path to enable on-demand mobility concepts, and has been the certification policy lead for unmanned aircraft design requirements, and has led the UAS type certification efforts. Thanks, Wes. That was a long one.
Thank you, Stan. I didn't mean for you to read that whole thing. That's
well,
great.
I think I cut everybody else's down, but this is also relevant.
I appreciate it. Thanks very much. You know, that's a really hard act to follow, because a discussion about the FAA and innovation is a little bit like military intelligence or cheap diamonds or whatever you want to, the paradox. But great presentation. Thanks so much. A good setup for me. So what I wanted to do today, while I have a little bit of your time, is to talk a little bit about the FAA's efforts to try to be proactive and enable new technology to enhance safety. We have found over the past 10 years or so, if we recognize new business models, new ideas, new technologies out there, and work collaboratively with those companies, we can actually have an impact in a positive way for safety, especially in the general aviation industry. And we've got a track record of that. So today I'll be talking a little bit about how we're taking that philosophy and applying it to try to enable some of the core technology pieces for eVTOL and simplified vehicle operations, on-demand mobility, whatever you want to call this, this great new world that we're facing that Uber Elevate is helping to promote. And I'll also just spend a little bit of time talking about some of the core technologies that we recognize we're better if we collaborate. Whether it's with NASA, industry, whoever, every time we've done collaborative efforts in the past, we always get a better result. So I'll be talking a little bit about that today. And I just forgot to put my first slide up there, so that's what all that said. The one thing that's really important for our applicants, for you as the companies coming to us with new ideas to talk about, is to keep in mind that there are multiple facets of this problem that we all have to tackle all at once. In other words, the aircraft that's going to go into the airspace that's going to fly in, and the people and technologies that will be actually flying it through the air are all part of the problem. And you really can't take a single one of those away and try to solve it by itself. A great example is whatever airspace you choose, that drives the equipage for the aircraft. And that equipage will then go into how good does the automation have to be to take that information from the equipment and make decisions to try to manage the flight path if the pilot is not expected to do that. So this idea of looking at pilot functions, looking at the functions that an air traffic controller might do, looking at the functions that are necessary to integrate into that airspace, and also the onboard automation, all of those pieces have to be sort of taken all at once together. And so that's really what this idea of simplified vehicle operations is doing. It's looking at integrated flight control technologies that can simplify the task of controlling the aircraft, taking data from the air traffic system through UTM or whatever means that is, and bringing that onto the aircraft to help the automation and whoever's monitoring the flight do that safely and to make good progress. So the challenge is real there. We have to work on these things together. I've found that many of the companies that have come to us have been sort of focusing on the aircraft technology and not as much on the air traffic piece, or how good does the automation have to be to actually replace the human being. So those are sort of key challenges that we need to be working on together, keeping all of those three elements in mind. But what if we looked at this space that we're looking at, this challenge we face together, what if we looked at it as just a continuation of what we've been doing over the last 20 years to try to bring new technology into aircraft to enhance safety? What if we just looked at it as the next logical step to reduce crew workload? We got rid of navigators, we got rid of radio operators, we got rid of many of the crew members that used to be on some of the older aircraft. We're down to 2 crew in most large transport category aircraft. And so this could just be a continuation of our efforts within the FAA to take technology and enhance safety. And so we see this as kind of that idea, this continuation. And we've had great success. We have a pretty good track record of bringing new technologies into general aviation in particular. We worked back in the 1990s with the Agate program, with NASA and with industry and academia. And that whole research project led to most of the technologies that are commonplace in your modern GA aircraft today, like the SR-22 from Cirrus and others. Those glass displays, the GPS navigation systems, the terrain maps, all of those things, the weather in the cockpit, all came from these proactive research efforts and collaborative efforts between the FAA and industry. And so we want to continue that. At the same time that we've been looking at that external technology integration, we've also been doing internal process improvements for the FAA. So we've been looking at how we can bring technology into the retrofit fleet better. So we have our approved Modellist STC process that we created. That's been very helpful in getting technology into the existing fleet. We're working with GAMA, with a lot of the other industry groups on trying to improve our certification processes. And so industry and all the international collaboration we're doing together with EASA has led us to this point of this Part 23 rewrite. All of these things have been kind of an internal look at the regulatory bodies to try to create an atmosphere where we are looking at innovation and trying to be more collaborative, try to inspire innovation. The reason that we're doing all this is because we know that it leads to safety improvements. You can look at our historical fatal accident rate, and you can tell that the past efforts that we've done to implement technology have had a positive impact. If you look over time here, we basically can see a reduction in general aviation accidents in particular. This has led to a really interesting phenomenon that's going on now, where not only is the FAA's internal view of being proactive towards technology changing, we also have found that there is now a trickle-up effect going on, where technology is being prototyped in small aircraft and then working its way onto larger aircraft. That completely has turned the traditional system on its head, where 30 years ago, 20 years ago, you had to wait until a piece of equipment was put into a military aircraft, maybe put into a transport category aircraft, and then became eventually affordable, maybe on about a King Air-sized aircraft, and then you were lucky if your general aviation airplane, if you could afford it. That has sort of turned on its head, and we have a whole new industry with the small unmanned aircraft industry, where technologies are being prototyped every day that can do these amazing fly-by-wire technologies in a very low-cost type of implementation. So the lessons learned from programs like the Harrier, prior X-plane programs, all those things are sort of coming together at the same time here. So we have a convergence of many factors. And that's really a good thing, because we collectively with you, with the industry, the FAA, NASA, all of us face probably the biggest change that we've seen in aviation maybe since the jet engine, and that is the implementation of unmanned aircraft systems into our existing national airspace and the implementation of this high level of automation. And so those things are certainly going to challenge all of us to make sure we're working together. So I wanted to get together today and just kind of talk a little bit about some of the proactive steps that the FAA has been doing to try to enable SVO or enable urban air mobility. We have been working with NASA and industry for many years, since the early days of Mark Moore's vision for on-demand mobility. And Ken Goodrich and us in the FAA and several other people have got together, and we have had several looks at this simplified vehicle operation type of concept. And so we've got those efforts going on in collaboration with industry and NASA. But we also, about 5 years ago, internal in the FAA, we made an acquisition of some R&D money. And we specifically started looking at research and development contracts that we could put in place to enable one of the core technologies, digital flight control technologies, in an affordable manner. And so we have roughly about 14 different contracts underway as we speak, and David Cizo, our test pilot in Kansas City, is leading those efforts for us at a technical level. Those efforts are really looking at specific implementations of digital flight controls and how we can enable that piece of precision flight path control in a way that takes that burden off of the pilot. We also have our internal FAST team. Andy Sapini here in the audience is leading that effort. That group is looking at the Part 23 rewrite that was just recently completed and trying to figure out ways, as Anna and Mel mentioned in the previous panel, what ways do the requirements need to be pulled together to create a certification basis for these new aircraft, and what would the means of compliance look like? And so Andy's group is doing a gap analysis of the new Part 23 and what needs to come in to change to those requirements so that we have a certification basis that can be broadly applicable and cover these types of new innovative technologies. So that targeted R&D and all these other pieces are sort of building together to try to help us go from just concepts, like we're talking about here at the conference, going to help some of the companies that are in development stages right now with new vehicles. So they're doing flight tests, they have full-scale prototypes they're flying to try to get to a point where they can move into a real operational use case for the aircraft. The key is collaboration, as I mentioned, and I'll put in a plug from Anna's earlier panel discussion on the importance of industry standards. We really need you as the experienced people in the companies to get involved in the development of industry standards for flight controls, for automation, and all of those efforts will be helpful to try to make sure we can document a minimum acceptable level of safety for these kinds of systems and to move the ball forward on that. We recognize, as the deputy administrator, or the acting administrator said, we have what I would call regulatory humility. We don't have all the answers for these technologies. We need your help, and those collaborative spaces for the industry standards are a great place to do that. We also want to make sure that you are helping us in those industry standard bodies to balance innovation and regulation, which is key. We can raise the bar on certification to a level where you can't bring any new ideas in, and that's definitely not what we want to do. We also don't want to relax the standards to a point where we have escapes from safety. That's obviously not our intent either. And as I mentioned, since we have all three components, the aircraft, the airspace, and the operation to consider, we're also pulling in our air traffic and flight standards folks into a lot of these efforts to collaborate. So I'll sort of end on this idea. This is a chart that shows, at least in my head, how all these things relate together. That is that there are cheap sensor technologies that came into the general aviation world from the automotive industry, from consumer electronics industries, that enabled avionics in general aviation aircraft to really advance over the last 10 to 20 years. That brought on great autopilots that we have now, a lot of envelope protection systems that are in general aviation aircraft now, and we're hoping for full authority augmented systems that can do full flight path control like fly-by-wire. At the same time, we had the evolution of the unmanned aircraft industry, where we went from really literally radio-controlled aircraft where you had to be in the loop all the time, to now aircraft that if you let go, they will just sit there with basic stability and hover, and then working on simplified integration with geofencing and other technologies so the aircraft can go fly a mission without the person actually having to be in the loop. As that moves forward and we do more UAS integration, we're working on better autonomous operations beyond visual line of sight, those kinds of things, and maybe eventually multi-aircraft operations. Hopefully that sounds familiar. We've talked over this course of the last couple of days with Uber wanting to do eventually, one-to-many type of operation with a monitor watching these flights from the ground potentially someday. So that little red line on there is sort of a notional "we are here." We'd like to enable eVTOL in the first concepts here with aircraft that potentially have a pilot on board, and then work our way through simplified operations and future integration, and eventually this idea of full passenger service someday. So that's just kind of a notional relationship of these technology enablers as I see them sort of fitting together. And so I wanted to kind of close with that. There's my contact information if anybody wants to get a hold of me, ask any questions about the research we're doing, or if you're interested in getting involved in some of the ASTM standards for automation, for flight controls, or for the ones that are supporting the Part 23 rewrite. And I'll end on that. Thanks.
Thanks, Wes. Thanks, Wes. All right, Wes is going to be followed by Dr. Noel Duerksen. Noel's worked at Garmin for about 14 years as an automatic flight controls engineer and test pilot, and at Hawker Beach prior to that, and he's currently working with the FAA on developing a certification path for advanced flight control and display concepts.
Thank you. Well, thanks, Wes, for the great introduction. What I'm working on is one of the research programs that Wes is actually funding. I also like to give quite a shout out to Justin, because he's basically done most of what we're doing here but he's done it on the military scale. But this has a different slant to it, so it'll be interesting to see how this all works together. So this is who I am. The problem statement is general aviation or single pilot operations have way too high accident rates. 60% of the accident rates are either loss of control or flight into terrain. Those are pilot error accidents. So if you can eliminate the pilot error, you end up reducing the accident rate by at least 60%. The secondary problem is it just takes way too much time and effort to learn to fly. Embry-Riddle says if you go to their school, it costs about $70,000 and 2.5 years to get to a commercial pilot's license. As we've talked about before, that's not a sustainable pilot pool for an Uber kind of operation. Currently, the pilot pool is declining at about 15% per decade, and that's accelerating because most of the pilots are older, not being replaced by the younger pilots. So how did we get here? In the past, we had pilots who were really skilled. They did everything in the airplane, and there was very little, if any, automation. Along came Nintendo Kid. Nintendo Kid likes video games. He writes software. He's very good at writing software. The avionics company said, we like this software, and started hiring these guys to make cool features. So now we've got a kind of a back and forth, a balance between automation and pilot skills. Roger Ramjet, he doesn't really quite understand what the box is doing sometimes, but as long as he's got a good backup to get him down, it's okay. The Nintendo Kid, he needs the automation to fly safely. And he's not really, what he's really interested in is a good autopilot to make him look good. So where are we going in the future? Well, you can see the trend here is that we're going to get more and more automation, and the piloting skills will get fewer and fewer. So Roger Ramjet is really starting to get a little bit kind of uneasy now. This statement here at the bottom is, too much automation degrades my stick and rudder skills. We see that statement in many, many accidents when the experienced pilots say, what is the problem? The problem is our pilots don't get enough stick and rudder skills because the automation is always operating the airplane. Nintendo Kid has a whole different attitude. He says, just get me there quickly and safely. I don't care about the flying skills. Sound like the Uber thing? So we created a new kind of flight control system. It's exactly the same thing that Justin talked about, but we came at it from a whole different point of view, which is kind of cool because we converged at the same conclusion. So I'm going to explain a little bit about how the flight control system works. It's a velocity vector command flight control system. If you move the stick fore and aft, and this is a fixed wing orientation instead of the hover, so we kind of mesh pretty well here. So when you're in forward flight, if you move the stick fore and aft, you change the vertical flight path angle. Centered is altitude hold. And in our implementation, we made it go plus or minus 7 degrees. It seemed to work well for the airplane that we put this in. Left and right motion, if you move the stick left, you command either a bank angle or a turn rate, depending on the velocity of the airplane. So you're changing the velocity direction, velocity vector direction. We allowed it to go up to 60 degrees angle of bank, which is quite a bit. And we changed the maximum allowed bank angle based on your speed because if you're going to hold altitude, you can't pull that many G's if you're already slow. So we had to change the control systems to make it all work together. The position of the speed command lever looks like a throttle. It's not a throttle. It's a speed command lever, just like Justin talks about. If you move it further forward, you go faster. If you move it further aft, you go slower. It's a speed command lever. And in our case, we said we're going to have a minimum speed of VREF because you can't, there's really no point in flying slower than that. And we have a maximum speed of V&E minus 10. Makes sense to protect the airplane. We built in a bunch of protections as well. Angle of attack protections, G-loading protections, bank protections, overspeed protections, ground collision protections, which makes it so that you can't lose control of the airplane and you can't fly into the ground. We had some interesting characteristics that came out of this. You can't fly slower than VREF without full power. You only get to the angle of attack limit when you have full power. Sound kind of like a hover kind of situation? This all kind of works together. It melds and blends. The maximum bank is reduced as the airspeed slows, so you end up with a turn rate command thing, which is kind of limited by bank angle. And you have direct command of the flight path vector. the pilot is not controlling the attitude of the airplane or the position of the ailerons. He's controlling where I want to go. So you move the flight path vector command lever and say, I want to go there, and that's where you go. If you want to stay going there, you don't move the lever. You put it at the end of the runway, and that's where you're going to go. There's no need to compensate for turbulence. The flight controls do that for you, so you don't have to be fighting the controls. So the result is that the accident prevention really works. If you can't lose control of the airplane and you can't run into the ground, that's 60% of the accidents that you've eliminated right off the top. We also found this system really significantly reduced the pilot workload, and it reduced the training and proficiency time. So let's test this. So we did a test, like Justin did. It's amazing how Justin just set this up really well. Thank you, Justin. So the airplane that we did this in was a Bonanza with a velocity vector control system. It had round dials on glass. It's the wrong kind of display for this sort of control system, but that's what we had. And we had a rudimentary moving map system. Our pilot, we got a tech rider with no experience flying an airplane. And I took her out to the airplane, put her in the airplane, and gave her about 15 minutes of ground instruction. This is how the airplane works. This is the control system. You move it forward to go down, back to go up. Move this forward to go fast. Move back to go slow. Turn left, turn right. Let's go fly. So then I gave her about 15 minutes of VFR instruction. This was the really interesting part because I reached over and I moved the stick all over. The airplane's doing this sort of thing. Now you do it. Move the stick anywhere you want. You cannot hurt the airplane. And she took me literally. She's slamming the thing around, so we're at 60-degree bank, 60-degree bank, climbing. She's all over. We're like Top Gun in a Bonanza with someone who's never flown an airplane before. She's ecstatic. So the next thing is I put an instrument training hood on. So this is a device like this. You can only see the instrument panel. You can't see outside. And I gave her about 15 minutes of instrument instruction, which is basically go to a course, follow a course, go to an altitude, follow that altitude. So what happened? It's time to go home. She thought it was pretty cool. Here's the instrument approach that we did. So she's still under the hood. She can't see out. And it's this approach is the runway is going north and south, and the final approach course into the runway is going to the west. So it's a perpendicular approach. We call it a circling approach. And I had her go to the final approach course, follow the final approach course, and track the thing inbound at 140 knots. That's over 2 miles a minute. And I'll tell you what altitudes to fly. So she successfully flew the approach down to 400 feet above the ground, which is the minimums for this approach. So now we are approaching the runway at 400 feet above the ground at more than 2 miles a minute with someone who's never flown an airplane before under the hood. At 1 mile away from the runway, I said, take your hood off, look up, and turn parallel to the runway, to the right. She looked over at me and said, what does the runway look like from the air? I hadn't bothered to tell her that. We're going to the runway at more than 2 miles a minute, and we're about a mile away. Turn right hard now. She slams the stick over to the right side of the, and we bank up into 60-degree bank turn. The airplane pulls 2 Gs. The throttle goes forward to hold 140 knots. I said, okay, you can stop the turn now. So she lets go of the stick. The airplane is 140 knots, 400 feet above the ground, level, and the runway is right over here. We're paralleling it. So, okay, now you can slow down to 90 knots, put the landing gear down, we'll turn left and do a base leg to land. It worked. The training the training requirement was significantly lower, and she didn't lose control of the airplane, so was fantastically confident with it. She knew she could do it. It's Justin's story with a high-speed approach instead of a hover. It works for all of these flight regimes. Thank you, Justin. Great setup. I really love your presentation. Can I give it next time? So this brings us to Wes. Because Wes said that he's got a bunch of programs that he's funding to develop this kind of technology, develop specifically the path to certification of this kind of technology. So what Wes's group is doing is they are proactively working with us in industry. And this is a different airplane. This is an Aviation, but we have the same control system built into it. I'm working with a company called Flight Level Engineering to do the same kind of technology development, but with a whole different purpose. The purpose of this is to develop a certification path to get this type of a control system into certified airplanes, because it currently can't be done. So there's a lot of questions that we have to ask, and we're using this airplane to do it. So what features are really required for safety? What are the display elements needed? Now, we did this with round dials on glass. It's completely the wrong thing. So currently we have airspeed tapes and things like that, but if the airplane is controlling the airspeed, why do you need to have an airspeed tape? If the airplane is controlling the attitude, why do you need to have an attitude indicator? All kinds of things like that. Moving maps become very important, and the symbology is probably quite a bit different on a moving map for this kind of display system. So we're figuring that out. What training requirements are needed? So Wes is also working to organize the training part of the FAA to come alongside with us to figure out what should the training requirements be. Because, for instance, a private pilot or even an instrument pilot check ride could be done by Diane, our tech rider, with virtually no training. So what's the point? What regulations need to be eliminated? This is what Anna was talking about. There's some regulations that just don't quite fit with this kind of control system. What regulations need to be changed? They're okay, but you can, as she said, shoehorn them in with a mallet. And what new regulations need to be created, because they just aren't anything that governs what we're doing. So, again, as Justin said, we don't get to have a mechanical backup mode. This isn't a system designed for Roger Ramjet. Roger Ramjet is not our target. So we've gotten a lot of interesting results from the Roger Ramjets who we've put in the cockpit, which have very different reactions than the Dianes, the technical rider. So if we had a backup, which was a direct mode or a mechanical backup, then we would have to teach the pilot how to fly the airplane with the mechanical backup, a conventional system. We would then also teach them to fly with the easy system, which doesn't take much, but teaching them to fly with the original system is the same problem we're trying to get away from. So we can't have a mechanical backup. As Justin said, it just has to work. The reliability has to be built into the system. We don't dump it onto the pilot when something goes wrong, which brings up the next set of questions that we're trying to answer is, when something does fail, what are appropriate flight control characteristics? How often should we allow the degraded flight control characteristics to occur because of a failure? And when they do, and what kind of oversight functions do we need to have to look over this whole system? Because our expectation is the pilot does not have the ability to diagnose system failures very well. So we need to have oversight, or Wes's group calls them runtime assurance functions. What do these functions do? Do they pop a parachute? What do they do? How often do we allow the oversight functions to take over? So this presentation has talked about flight controls in particular, but there's a whole ecosystem in the cockpit of things that have to happen. There's the displays, which I've mentioned just a little bit, the navigation system, monitoring of the systems, how the aircraft responds to failures of those systems, all of that sort of stuff, and we could go on, and I've got a bunch of presentations, but I'm out of time for this one. So next I'd like to introduce Greg Bole, who's been here before, and well, you're going to introduce Arthur.
Yeah.
So there we go.
Thanks, Noel. All right, Greg Bowles is going to wrap it up for us. Greg is the Vice President of Global Innovation and Policy at GAMA, and among many other things, he leads GAMA's Electric Propulsion and Innovation Committee, as well as the Simplified Vehicle Operations Committee. Thanks, Greg.
Thanks very much. I appreciate it, and I will get us wrapped up very quickly. So here's what I heard today. We take these humans that are called people, and we turn them into pilots. So how do we do that, right? We take a person, we add knowledge and information to them, we add flight experience, we medically check them, and all of a sudden they're a pilot, right? That takes a lot of time and effort in some of those buckets because of what they must do. Today, an FAA single-engine rated commercial airplane pilot, which is a rather extensive set of training, is allowed to fly an aircraft from a small single engine up to a pretty complex, large single-engine airplane. So that's a PC-12 on the other end, which is a over 10,000-pound vehicle. And that is the same rating So that's a big spread of things that person can do. One of our goals that we've talked about as a broad eVTOL community is to design these vehicles such that they wouldn't require any more skills than taking a person with those kind of capabilities, adding, and by the way, that's the knowledge, the medical, and some additional requirements that would come on top of the operator in the 135 world. And we want to add an endorsement, an eVTOL endorsement, which would include how to operate an electric aircraft. What are the particulars in how to control these in simple vertical flight, and controlling the automation systems. This is not that out of the ordinary. If you look at, for example, a Seaplane Rating, the Seaplane Rating is a relatively similar package where you're learning about a new environment and new characteristics, the way the aircraft handles, and new equipment. So the amount of information, if we design these vehicles properly, as we've kind of been discussing here, and all the panels have discussed, is certainly where we're aiming. I'm going to skip through all of these slides because you've heard about how the flappy things used to move, and now we're going to control flight path. And I want to talk about something to wrap this up. So today, the cockpit works this way. We've got a suite of sensors feeding the autopilot. When one of those sensors goes bad, what do? We shut down the automation, right? We say, we have a miscompare, we have bad information, shutting down the information, pilot giving you an airplane during a unfortunate circumstance, and it's a pretty big handful, and you have not been flying the aircraft actively, and now I'd like you to jump in when it's a little more than traditionally difficult. Okay? That's today's state of automation, and that's the way the policies and the guidance have been written, because we haven't had confidence in this new concept, these new technologies that have only been around about half a decade, half a century, right? It's been about 50 years since we've had these things. Where are we headed? So the kinds of technologies we've talked about in the F-35 and what Noel just discussed require this kind of architecture. So we've got multiple sensor suites that are fused together. We have multiple flight control systems that are all talking. And when we lose heading information in one of those fusion suites, it says, hey, flight control system 1 and 2 are not happy with the information coming off of one of our sensors. So we'd like to highlight that to the pilot and say, hey, Mr. Pilot or Miss Pilot, you no longer have reliable heading information on one of your sensor suites. So we think next time you land, you probably have to have some maintenance done before you dispatch as an awareness item, right? Everything's functioning normally, but there's some awareness that there's a maintenance action to be taken. That's where we're trying to get, right? In this case, the pilot says, cool, we'll hang on the pad a little longer. So what I've done here is I've taken the training, the FA training, and we as a group, we've broken this into 12 essential skills that pilots pick up through the flight training and navigation. The FA's basically broken pilot training into chapters. We've gone a little further and subdivided some of these tasks. These are essentially the skills that a human takes on to operate a vehicle. And so if you say that human is a meat processor functioning switches and levers, that can be replaced by an electronic processor in some of these functions, end to end. So instead of me throwing the human back in when the function fails, we want to make a particular function reliable end to end, because some of these are easier than others. So imagine if navigation, for example, were automated end to end. Today, we really rely on navigation. We don't look out and do a lot of map navigation nowadays, right? We're not doing a lot of dead reckoning any longer. Navigation's a pretty mature technology. On the other hand, I think we all talk a bit about concerns in detect and avoid, right? That's something we're still figuring out. I think some would say, oh, we're there. Others would say, no, we're not. So of all these skills that we teach pilots today, where do we as an industry feel that we are ready to automate? The answer is those certainly go away. I think there's unanimous agreement amongst some really smart folks that these functions are primed to be automated, and we're going down these paths right now. These are up there to be discussed as well. So the question becomes, how long would it take to train that pilot? The pilot that has to have decision-making, pre-flight planning skills, or somebody has to do pre-flight planning, maybe not the pilot. Somebody needs to inspect the aircraft for airworthiness, maybe not the pilot. Somebody needs to understand emergency procedures and evacuation. That is a set of skills that allows much abbreviated training. And that's where we're trying to head.